The method of moments approach to estimating parameters focuses on of course, the moments of the data, and it really focuses in on the body of the data. Another approach here is to select the parameters to make the observed sample the most likely, hence the notion of the maximum likelihood in the title. That in some sense of having the most likely one, that we've got better parameters. That somewhat suggests that, boy, this random sample is truly representative of what we've got. And there's two different views that we need to be thinking about here, and one of them is that before the sampling happens, so we don't have x1 to xn. Instead, what we have is a joint probability of the values that are to be sampled. Now keep in mind, if it's a random sample, then each sample is stochastically independent. And so that simplifies things a little bit for us, that our joint distribution of all of these in randomly selected values then is going to be equal to the product of the marginals of those n ones. Now also keep in mind that our parameter is a random variable, so here we're assuming that in this particular expression that this is conditioned on the parameter, right? Now, after sampling, we know all of our data points. So now the goal is going to be, well, to select our parameters to maximize the likelihood, and the likelihood being expressed here as by our joint PDF, and so think about that back as our product of all the marginals. So let's go back and illustrate this with our traffic data model, and particularly that exponential model that we were looking at, that our conditional here was equal to lambda e to the minus lambda x. And remember from our method of moments that our lambda was equal to 0.2, and it turned out that our 1 over lambda was equal to our set equal to our x bar, and that's how we came up with that particular value. Right? For the maximum likelihood approach in this estimator, first step is to construct our product, this guy right up here. Okay, so for this specific case, our parameter is lambda, and so that's going to be equal to our lambda e to the minus lambda x1 times lambda e to the minus lambda x2, so on and so forth, up to lambda e to the minus lambda xn, right? Independent, identically distributed. So each of the xi's has the same model here, same parameter showing up, and then you get the x1 through xn. And so now what we're going to do is we're going to define our likelihood function. We'll call that L. And it's going to be equal to this guy right here. So that's lambda to the n and exp. So, and then all this stuff, right, e raised to that, all that stuff, which is going to be, after we factor out the lambda, the sum of all the xi values. And then what we want to do is to choose our lambda to maximize our likelihood function. And there's two different common ways that we might approach that. One of them is just to go direct here for the function, take the derivative with respect to lambda. There's only one parameter here, so really that could be a full derivative. Set it equal to 0, solve for lambda, and we get it. Another approach is to take the log of our likelihood function and do the derivative at that level. And of course the switcheroo is appropriate because it makes life easier. And isn't that what a lot of the shortcuts in math are all about, is trying to do something that's a little bit easier. Same thing we'll end up solving for lambda. Now this approach is always going to get us the max possible value for lambda. So if you're trying to set an upper threshold value, this is a good approach, as well as being potentially a tractable one. So let's look at that here for this case. The natural log of lambda, or I'm sorry, natural log of L is going to be equal to, well, we got this product, right? And so take the natural log of a product becomes a sum, and we'll have n times the natural log of lambda minus lambda times the sum of the x's. And then when we take the derivative of that, right, and we're taking the derivative with respect to lambda, right, so this becomes n over lambda minus the sum of the xi, and we're going to set that equal to 0, solve, and you end up with that 1 over lambda is equal to 1 over n, sum of the xi's, and that's x bar. And that turns out to be the same as before. You might think, well, we just did a whole lot of work and we didn't get any new information, but we did get new information. And that is that not only for the exponential model are we preserving the moments or the body of the distribution, the mean value, but we are also finding the maximum likelihood at the same time, right? That we're selecting a parameter where we're making this observed sample the most likely. That sounds great, and what your textbook does is going to illustrate this same approach for a couple of more examples, but I'm going to jump to one of the complications that arises out of using the maximum likelihood estimator. In the classic example for illustrating the complications of the maximum likelihood approach, you'll see in the textbook as well as what we're going to do here, and that's going back to, as an example, the uniform distribution, right, to our traffic data that we were looking at before. Right, well, there's our, let's call it this time parameter A, our maximum value here, and we're plotting our function, and that has to equal 1 over A, right, for this total area to be equal to 1. Now, we have to keep track. We're going to do multiple plots here. So what we're plotting in this one here is just a distribution of x, right? And what we're going to do in a moment is a different kind of a plot. But it's easy to get the two confused. And also critical to note is the domain for x has to be between the two bounds. These are the two parameters. And we can always shift them around, hence I think of it as only just a one parameter type model, and that's the upper bound. Right, now, we found out that from the method of moments that A was equal to 2x bar equal to 10, so A was equal to 10, which made sense. We were preserving the centroid. Right? Now, from a likelihood function perspective, or that's the product of the marginals given our parameter. In this case, our parameter is really A, so let's turn that into an A. Right? And that's going to be equal to 1 over A, but product of those from 1 to n, so that's 1 over A raised to the n. Right, but note, for this to work properly, right, maximum likelihood of the observed samples, we have to have that our x1 value must be less than A, and our second one must be less than A, all of them, right, including this max value, have to be less than A, or could presumably be less than or equal to A. Right? Because remember, in the maximum likelihood approach, you must end up with that being the case. And so if that's going to work out to be that way, see, with method of moments, we were preserving the centroid. So if we had in our model one that was outside of it, a data point outside of A, that wasn't great either, but we were preserving the centroid, and if that's what we cared about, then maybe that was okay. But in the maximum likelihood approach, we're trying to say that this particular observed set is the most likely outcome. We're maximizing that likelihood, and so we run into this little wrinkle here, and that's also illustrated. Remember, we're going to take a derivative of this thing, right? So we're trying to find a slope, and because of this feature, if we plot L, our likelihood function as a function of A, then we end up with a discontinuity that is showing up right here at the maximum value, right? Because as long as A is outside of that, then this works, right? And so we're going to end up with a function that looks like that. Back here, we're sitting down right there. And so what's the slope then? That's the problem. We have a discontinuity in the function right in here. Right? And so because of that, you end up with a kind of goofy thing of, well, what's the slope of L at a discontinuity, and how do we handle it? Well, here it's a fairly straightforward way to handle it. We know that we have to have that A has to be greater than xi, and so we'll go ahead and just set A equal to x max, and that would be equal to 10.1. And you know, of the two approaches, there's not much of a difference here, right, in this particular case, but that's not always going to be the situation. And it just emphasizes that these threshold values are difficult to estimate. Right, it requires, in essence, complete knowledge in the tails. That we have to have lots and lots of data out there in the tails, but we don't really ever have complete knowledge out there. Overall, big picture is that the theory of maximum likelihood does better than method of moments. We've only shown cases so far where you get essentially the same result except for this sort of pathological problem with the uniform distribution. But you'll see in the text, as they look at a couple of different other distributions other than the exponential, that you get the method of moments estimators and the maximum likelihood estimators to be the same. And that's not always going to be the case, right? There's just a couple of situations there. So let's summarize this in one final piece. With the following, and let's set up this as two different tables. that our method of moments approach is going to emphasize the body of our distribution, and tail parameters are difficult. Right? Dependence turns out to be difficult to handle with the method of moments. And it requires us sometimes to solve nonlinear, simultaneous equations. Never a fun thing, right? The maximum likelihood approach tends to be more neutral to the body and to the tail. Dependence is easier to handle so long as we can actually get mathematical forms of the dependent relationships, right? But we end up with one large optimization problem. And you can see that also in the text when you look at some of their examples. Kind of leaves you with the overall big question of, well, wait a minute. So which should we use? Right? That's the bigger question. And the answer is yes. Go out and do well. Right? Well, no, it's not quite like that. Rather, there's going to be some cases where there's a straightforward approach to which to use. And fortunately, in many cases here, both of these two approaches for our classic situations are going to tell us similar kinds of information, and that, in other words, the method of moment estimators and the maximum likelihood estimators will be identical. The subtle differences are going to show up here as we get into talking about bias in the estimators and error in the estimators, and we're going to do that here shortly as we get into talking about sampling distributions and what these two approaches tell us that. So there is an answer coming from a short-term practical kind of standpoint of what exactly should we do in this particular course, how does this apply to us, and the answer is we're going to go take a look at a lot of these statistics such as the sample mean, sample variance, and sample standard deviation, and start asking questions about how representative are those for the particular data set that we're looking at as a representation of a population.